All right, last week we were looking at ionic bonding. Okay, we saw that when you build fluorine, the valence shell is needing one electron. Lithium's valence shell has one electron. So lithium is going to donate one electron to fluorine, which I don't think we wrote that down.
We did, but you said it.
Okay. Lithium donates. Fluorine accepts.
Damn, man.
When they do that, they are tightly connected in an ionic bond close together. In water, these will come apart. And they'll come apart so that fluorine keeps the electron that it accepted, and lithium does not take back the electron that it donated. So fluorine we call -1 because it's gained one negative electron.
But why does it have one negative and why have the other one plus? Don't they be opposite? So because the Li gives one to the F, it needs to be minus. No, I don't understand that part. Can you explain it again? No, because.
Lithium is +1, a cation, because it's lost one negative electron. So if it loses something that's negative, it is more positive. And that's why it's plus. Anions gained something negative, so it is more negative. Okay, so it's the opposite of what you think. We think of losing as being negative,
So losing will be more.
but in this case, it's. Remember that electrons are negative, and that's what's moving. So if you're gaining something negative, you're more negative. If you take away, you lose something negative, you're more positive. Okay, and we're going to do practice with these. Okay, some characteristics of ionic bonds. One is they come apart in water. To make ions. Okay? Whether it's a cation or an anion. Okay. Ah! Whoa! Sorry. Okay. They form salts. Okay, so LiF, that's what we made. This is a salt. It's called lithium fluoride. NaCl is a salt. This is the salt that we eat, called sodium. Chloride. KBr is a salt. We call this potassium bromide. Do you guys see a trend? Look at the names. Lithium fluoride, sodium chloride, potassium bromide. They all end with IDE. That helps us to know about ionic bonding.
So all three of them are ionic bonds.
Yes. These are all ionic bonds. And even though sodium chloride, this is the table salt that you eat. Okay, this is the salt that you put on your food or in your cooking. These others are still called salts also. Okay. These ionic bonds are brittle. Do you know what brittle means? So it's hard, but easily breaks. When we say that it easily breaks, we are not saying that these come apart. We're saying that a gigantic cube of salt breaks up into small pieces of salt. That's what it means, right? You can take a big thing of salt and pound it easily and it breaks up into little pieces, right? But these still stay together. They don't come apart until they're in water. Only water will make them separate. All right. So, yeah, it's a little dirty. Ew. Hold on.
I already found it's
That's
two.
fine.
Which one, the long one or the short one?
All right. Oh, there's still dirtiness in there. All right, so this is some salt for my lunch. Okay, so you have the little pieces of salt. Okay, if I add a little bit of water, whoops, that was too much water. I did not mean to add that much water. Hold on.
Do you need help, Miss Judy?
All right.
The salt is soaking. Oh, I know what
I'm getting water everywhere. No, that's nasty. I'm not drinking it.
I taste salt very specific, but it tastes terrible.
I need to add some more water.
Yeah, because it doesn't.
Miss Judy, you know, can I ask you something what happened to me I was in California? No. I taste salt water.
Yeah, salt water tastes nasty.
Yeah, I got a cough a little bit.
All right. So I'm going to now. Good. Yes, it is separated. It's dissolved.
No, it means like the salt has been dissolved.
Come on.
So do you see the salt anymore?
No, there's no salt. It's gone. All gone.
Oh. Now we can
The
see.
salt is
Okay, so the salt is dissolved in it, but it's still there. So what I'm going to do is I'm going to put it on this hot plate,
and then fire.
and hopefully it will boil this period without hurting me.
Miss, but can we do the same but with sugar? Can we? Yeah, right?
I just put this into the jail house.
Okay, so it's brittle. It's hard, but it will break up easily. Okay, and it will, you can like crush it pretty easily also. Okay, so those are some trends for ionic bonds. Now there are other types of bonds. Okay, there's covalent bonds, which normally we would learn about those also, but we're not going to worry about them this semester. There's van der Waals bonds, which are different levels of very small attractions between different atoms. Hydrogen bonds. Hydrogen bonds are responsible for DNA being in a spiral. If it was not for hydrogen bonds, DNA would not be in a spiral. And that was one of the most difficult things for Francis and Watson to figure out, like the shape of hydrogen. It was because of work that Rosalind Franklin did that discovered that it was in a spiral, and that solved all the problems. Okay, so we're going to look at the periodic table, and this will help you to predict how the atoms are going to bond together. So the first thing that we're going to do, okay, we're going to draw lithium up here, okay? Or let's just do hydrogen. Hydrogen is there. And I'm not going to worry about the protons and neutrons. Let's just look at the electrons. So how many electrons are in hydrogen?
One.
One electron in hydrogen. Yes. What about beryllium? How many electrons are in beryllium?
5.
There's 4 electrons in beryllium. So 1, 2, then you need the next ring. 3, 4. We're going to skip these in the middle here. These are called the transition metals, and they can have more than one ion. So we're going to skip those. Let's go over to boron. How many electrons are in boron? 1, 2, 3, 4, 5. And because I write big, I'm going to make my carbon up here higher. How many electrons in carbon? 6 electrons, right, K-Ray? And then my nitrogen down here. How many electrons in nitrogen?
7.
Oxygen. I'm going to do up here. This is the O for oxygen. Do fluorine here. I'm glad I didn't worry about protons and neutrons. That would take forever. Right, K-Ray? How many electrons are in fluorine, K-Ray? How many electrons are in fluorine? And for this last column here, I'm going to do neon.
So that's gonna be, that one is happy, no? You have all of them.
Correct. Neon will be happy. Okay. I'm also going to do lithium over here because hydrogen can be a little bit different from this column sometimes. So, and lithium only has 3 electrons, so it shouldn't be too bad. All right. So, something important that you should notice. How many valence electrons are in lithium and hydrogen? How many valence electrons? Valence electrons are the electrons in the outermost shell. One valence electron. How many valence electrons in beryllium? The outer shell has 2 valence electrons. How many valence electrons in boron? Has 3 valence electrons. How many valence electrons for carbon? 4 valence electrons for carbon. How many valence electrons for nitrogen?
5.
Can you poke K-Ray so he stays awake? How many valence electrons for oxygen? 6. How many valence electrons for fluorine?
7.
How many valence electrons for neon?
9.
8, which means he's happy. And what you will see if you draw argon and krypton, you'll see that all of the valence electrons in this column will be 8. These are 7, 6, 5, 4, 3, 2, and 1.
All of those gonna have 1. So what about the one that it says FR 87? No, right? What?
Let's go ahead and draw real quick. Sodium and potassium. They're going to be a lot, but it will help us to see also. Okay, sodium. How many electrons for sodium?
11.
You guys should be drawing this also
You're right.
on your periodic table. I'm doing it, you should be doing it. You should be thinking about it and drawing it.
Got it.
Okay? Look at the students who have A's. What are they doing? Do what they are doing.
Well, I don't have an A, but I'm drawing.
Potassium has how many electrons total?
Why?
They have 19.
19. I'm not going to be able. Let's do. There's the last one, 19. Woo! 19 electrons. How about if you sleep, I'll make you draw francium.
Ooh, I can do that. I would do that.
That's francium. 87 electrons.
Oh, no.
Or maybe we'll do like one of these radioactive ones down here.
Please don't.
No. We're good. We got it.
Please don't.
Okay? So we notice that here in the first column, they all have one valence electron on the outside. Okay? How many energy levels does hydrogen have, or how many orbitals does hydrogen have?
One.
It has one orbital. How many orbitals does lithium have?
Two.
2.
What? Why? I'm just like guessing. The ones that inside we count now, right?
Okay, look at sodium. 1, 2, 3 orbitals.
So the insides are called orbitals and the outsides are called, what do you say? 3 and 8. We don't have to. So the other one will be 4.
How many orbitals for potassium?
4.
There's 4. So notice lithium had 2 orbitals. How many orbitals for beryllium?
2.
It also had 2. So when you go this way across the row,
It's gonna be the same.
they're all going to have that number of orbitals. So this row is going to be 5, 6, 7, 6, 7. Okay? Because this whole group down here fits right between here. If we were to extend the periodic table out even more, we would take these and fit them right in between there, and then it would be a super, super long periodic table. That's why they just took this group out and put them at the bottom.
I know why. Because I can see that you can see 57 and 72 of the words.
Okay, so you need to know. All right, so you need to know the columns show you valence electrons. The rows across show you the number of orbitals or energy shells. And something that's very, very, very important. The number of valence electrons determines the elements, characteristics. It determines Like, how reactive is that element? Will it react quickly? Will it not react quickly? Will it, like these? So these all have 8 valence electrons, so they will not react. That's why they're called the noble gases.